Okay, good morning to the few of us here this morning. And maybe the number will increase exponentially as the time marches on now. We were listening to Helplessly Hoping, the new anthem of MJC for the year 2003. Confusion and chaos. Okay. It's that kind of morning. We'll blame Debbie for that. Okay, we have questions perhaps on rational expressions. I don't know what kinds of problems we have with that. Okay, Michelle.
What? Yeah. I just had a question, because I did all the homework and it was fairly okay to do.
Now you're feeling like maybe something is wrong?
Something might be missing.
Oh, okay.
Were we supposed to, because like 15 through something 30, no, 23.
Okay, 15 through 23.
Were we supposed to put like let x equal something?
Not equal.
Or not that one, that's not what I wanted.
This is where on 15, or it's actually 13 through 20,
that's not
where you were finding the value of the expression, letting x equal a particular value. Now,
right.
On the restrictions, whether they were in number 5 through about 12, or 23 on.
Yeah,
to find the restrictions, and I think this is a point where you really have to understand what's going on here. The restrictions are found by taking the denominator and setting it equal to 0. Mm-hmm. So in essence, you're creating an equation. You are saying, if this denominator was equal to 0, then x would be these values. So to illustrate, no shock, this is going to be interesting. Okay, let me try this again. Like starting one of those statements to illustrate and then can't do anything. To illustrate, let's say we had x over x squared minus 1, just as a typical expression. In that expression, I'm worried about a denominator being 0. So I will set x squared minus 1 equal to 0. Now I'm doing this because I'd like to find out what value makes the denominator 0. So in doing that, I will factor and get the following. Now those are solutions to that equation I created. Now this is where you get into that quandary. Okay, you've told me x equals 1. X equals minus 1, give you a 0 in this. And now we're going to say what? Restrict the domain. So your restriction is going to be exactly these values that you just found made that denominator 0. So restriction, x cannot equal 1 and x cannot equal negative 1 because they make the denominator 0. Now there is no simplification I can do in that problem. And it was not an equation, and that is part of the dilemma. Because you start with a non-equation and then do what? Immediately create an equation to find the values that you can't have. That's a rather interesting little potential conflict. Find out what you can't have and then don't get them. Yes?
Okay. I understand that. But at what point do you do that? After you've factored it and before you've canceled out?
Yes. The question was, when do I go through this process? When you see these expressions, this would probably be an ideal first step. Just ask, when's the denominator going to be 0? And restrict those values. You, in the process, typically are going to have to factor. So you might argue your first step could be actually rewriting this as a factored expression and then point out I'm interested when this occurs because I am not allowed to do any canceling here until I've done what? Restricted the variable so that I have not reduced 0 over 0 give you another example. Little different one, and I'll change it just so that. Nah, I like this one. That's a better one. Do you recognize it? Now, in this process, if I do the first step, which is factor everything, that was a difference of cubes. And so I have factored this so that I now have x minus 3 over x minus 3. Now, I know what's going to happen in practice. You're going to see this and reduce them. But what is really very important prior to that step, to set x minus 3 times x squared plus 3x plus 9 equal to 0. Now this happens to be what? A prime polynomial. Now one of the things that's not clear at this point, is there any value of x that will make this equal to 0? And the answer is yes. Okay. Now it may not be in the reals, may be in the complex numbers, but we know every second degree equation, and that factor is a second degree expression. So I know that this is true or this is true. Now it's not factorable, this right one, but it's still, that would make this product equal to 0. So this first one, x equals 3, is going to be a restriction. So it seems a little bit contradictory. You get to this point and say x equals 3, and then what do you immediately have to say? Restriction. X can't equal 3. And that seems to be confusing for many people. Now let me come back to here. This particular trinomial in the set of reals will not be 0. Okay? Now what I did is a very quick mental check that I did in my head where I took this coefficient and squared it. And then I subtracted 4 times this times this. So I had 9 minus 36, and that turns out to be negative. So that told me something that we haven't talked about yet. But it told me that the only values of x that will make this 0 are in the complex numbers, not the real numbers. So it turns out there is only one restriction here. Now, there is no way that you would know that out of hand. So this problem was pushing beyond where you should be at the moment. But the reason I wanted to come back to this is only after you've gone through this analysis are you what? Really in a position that you can now say this. And again, my reminder to you, that physical process of drawing a line through that factor is important because you aren't canceling the terms, you're canceling the entire factor. So you can't sit there and line out the x's and line out the 3's. If you do that, you're telling me that you're canceling terms rather than factors. I like to put a 1 left for those. And so this becomes 1 over x squared plus 3x plus 9 with the restriction, what? And x not equal to 3. Okay. Does that answer the questions that have been addressed?
What do we do for number 27?
27?
Yeah, the answer was x minus 1 over x plus 1. So x can't equal 1 or negative 1?
Whoa, 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 whoa. Okay. You say, first the problem number?
27.
27. And whatever
Let
the
me get
problem
my-
is, you're telling me the answer is what now?
X minus 1 over x plus 1. So,
Okay, now, first, just in the basis of what I have here, there is an implied restriction. Note, whatever else happened before this, x cannot equal what? Negative 1. Could, on the basis of what I'm seeing there, x equal 1? Well, based on what I'm seeing there, that's reasonable. But it depends, because the numerator can be 0. Denominator, no. Numerator, yes. But the interesting question is, where did this come from as an answer? So at 27, I need to look at the problem and say, what was the problem I had? Now, is it one that lends itself to verbalizing? Michelle, can you give me the statement of the original problem, or is it too convoluted? Numerator.
x plus 1 in parentheses, x minus 1.
Uh-oh.
Over
Okay.
x plus 1 in parentheses squared.
Okay. I see what you were asking. Now, with that said, what is clear?
X can equal negative.
Well, x cannot equal minus 1 here. That's okay, and it covers both these. So is there any restriction on the fact that x could equal 1? No, that's certainly a possibility. And if I wanted this fraction to be 0, x equals 1 would do it. So a restriction in the denominator is very different than what will make the numerator 0.
So we're just looking at the denominator.
Just the denominator. But again, remember, what you were given was a rational expression. But it was an expression, not an equation. We set the denominator equal to 0 to get the restriction. So we created an equation out of part of the expression to find out what would make this problem not work. And then we made sure we didn't do that. Okay? It's a little bit, I remember the first car I had. It had an engine in it that was rather old, and I should have been restricted in the speed I drove. If you were going to drive 70, something bad was going to happen. So you should not drive 70. Didn't dawn on me that there might be a problem like that, so I drove 70. Next thing I knew, the engine wasn't working and had to be worked on in a serious sort of way. I took care of driving for about 6 months. We have restrictions that are inherent. You know the restrictions, so you shouldn't then do it. That doesn't mean we don't do it, but it does tell us why we set this equal to 0. Other questions on these problems?
37.
37.
Again, the factoring is right. I just want to make sure that strict restriction is...
Okay, let's see what we have in 37. Let me make... This is 6-1, isn't it?
Yes.
Okay, let's look at the problem. Okay, we've got 9r squared minus 4s squared. That's nice because what do you see, I hope, when you see that immediately? 9r squared minus 4s squared. What did you see?
Difference of squares.
Difference of squares, right? 3r quantity squared, 2s quantity squared. Then in the denominator,
Factor out 3.
a GCF of 3. Agreed? Now, this is a little different because you can't just restrict a number.
Right.
I think that's what I'm hearing as a question. Is that correct? So number 37. So let's write that. 9r squared minus 4s squared. And that is over 9r plus 6s. And just a comment here. I don't know if I want to call this wishful thinking, but you see what you have in the numerator? If there's any hope, what does it tell you, since this is going to be a plus here? That you're going to have your best hope is this. That's the only way you're going to be able to reduce it. So the question is, can I write 9r plus 6s as something times this? The answer is 3. So even if you do not see the GCF, you can work backwards if it's going to work. If you can't get this binomial, there's no hope of simplifying that expression. Now, clearly what we want to do is cancel these two binomials. But before we can do that, we have to ask, what will make the denominator 0? So I'm going to set 3r plus 2s equal to 0. And that's sort of an awkward, because you don't have a 2 or a 1 to restrict. What you say is that 3r is equal to negative 2s. r is negative 2/3 s. So your restriction is going to be r not equal to negative 2s over 3. Now, if you restrict that way, then you can do what? Cancel those two factors and be left with what for an answer? 3r minus 2s over 3.
Would you have to restrict the s? I mean, s.
No. The question was asked, do I have to restrict s itself? No.
So it would just, you could take one or the other, so you restrict r.
Well, I'm just saying, whatever s is, r can't be negative 2/3 of it.
Okay.
Now, question. If s is 0, what does this involve? If s is 0 and r happens to be 0,
Then
you're
it's
in
gonna
trouble.
be 0, right. So r can't be
Okay,
0.
but then that would say r is negative 2/3 of s. S at 0 creates an interesting kind of dilemma here, because we usually think of something like, example, s is 3. If s is 3, then you can't have r equal to what? Negative 2. So it's not so much the restriction on s, it's what r can't be given a particular s.
Okay.
Now, the downside of this is we have what appears to be a ratio, 2/3 of s involved, a negative 2/3 of s. And if you have s at 0, you get r of 0. And that's going to make that whole denominator 0, and then you're in trouble. So I guess you could argue there, r and s cannot both be 0 at the same
That's
time.
what I had originally, yeah.
But that's covered down here, because if s were 0, r would be 0, and you can't have that.
Okay.
There's quite a difference between this kind of statement, where you're restricting a relationship that exists between two variables, and what we had right here that you can see behind me, where we said x could not equal negative 1. That was a nice numerical value we could restrict. Okay. Other questions? Or are we? Yes? 6-1. Okay, 61. I'm going to have to turn the page. 61. Okay. Oh, this is, we did what, 62 yesterday in class?
Yeah, I think so.
This is just like the 62nd problem we did, isn't it?
Similar.
Similar. Okay, there's a little wrinkle here that makes this one a little bit nicer, because you can see in the m squared minus n squared. Do you see m minus n times m plus n right there? The difference of two squares? And then if you take a minus 4 out from here, you get an m plus n. Now what about down here? Well, you factor out a 2 and you have m minus n minus 4. And that is rather interesting. Okay, I don't know if anything good's going to come out of that, and I guess I have room to still try to use some space here. So let me write what we have. My first reaction was that this isn't as interesting as it may indeed turn out to be. So let's see if something is hiding here. Okay, here's the expression. Now let's do a little bit of shortcutting here just to see what we have. The denominator, there's no question, I can take out the 2. That intrigues me because I have an m plus or an m minus n and a minus 4. I have interesting idea. Okay, what do we have up here? We know we have an m minus n and an m plus n. I think I'm going to write that as the plus there and this one as the minus. Oh, this is always dicey when I'm trying to clean up a clean board and make it a mess. Not that this is too much of a problem, but there we go. And then what do I have here? A minus 4 times what? M plus n. Ah! Now, this is an interesting problem because what happens if I pull out the m plus n? What do I have left? The very same thing that I have in the denominator. Again, how am I going to do this? I'm going to put a little loop around here and a little loop around here. That's a common factor for the first product and the second product. So lift that out, and what am I going to have left? M minus n minus 4, which is right down there. So as far as the answer is concerned, that is just going to be m plus n over 2. However, what do I have to worry about? The restriction, when is this going to be 0? Well, when m minus n minus 4 is equal to 0, the restriction is going to be m not equal to n plus 4, because that will make the denominator 0. So if n is 0 and m is then 4, that would be a restriction. Couldn't have it. Again, if n is 0, m is 4. Well, if I put 0 for n and m at 4, the denominator goes to 0, and that can't be allowed. So you're right. That is a good question. We okay there? Okay, one more thing.
Since you have m plus n twice, how did you make it just 1?
Uh-huh. Okay, Debbie, I've got to travel. I'm going to have Debbie go back to the document cam because that's going to allow us to make a smooth transition. That was the mess we had. And the question is being asked, and I'm going to rewrite the line that is being addressed here. I have m plus n times m minus n, and then I have a minus 4 times m plus n, and then that is over what? 2 times m minus n minus 4. Do we now have it written correctly? Now the question, what magic am I doing up here? Okay, I'm going to ask you this. If I have a times b minus b, now hold on, let me think for a moment. I have a here, so I want a there, minus c times a. So I have the a and the outside in both spots. Distributive property. I can factor that into a, and what's left? The b and the c, agreed? So let's put a was what? That, b is this, c is this, and a is that. You have to watch that this is in maths. Now, the a was what? M plus n. Now, what is the b? The m minus n, there's your b, and what's the c? I'm going to put a parenthesis here. Does that make it easier to see? So, just a little, not a lot. If I multiplied with the distributive property, I would have what? M plus n times m minus n. Then what? M plus n times minus 4, which would be, just flipping it, minus 4 times m plus n. A reluctant okay, not a, oh yeah, it's like, if you say so. Anything else I can respond to there? Would it have made it easier if I had the m plus n switched right here? Had m plus n times 4?
Well, I understand how you cancel the m minus n minus 4.
Because I have it in both the numerator and the denominator. So you're saying you're comfortable with this.
Yeah.
Okay.
But the 2m plus n on the
Here?
top.
The top.
That one.
Yeah.
The other one.
But they are pulled out by the distributive property. Okay, let me try something else. Okay, I have 2 times 3 plus 5, and I'm going to down here have 8. Now, when I multiply the 2 times the 3, and then I multiply the 2 times the 5, that was like my original problem. Now, do you feel comfortable with this? Where did the other 2 go? Isn't that the same question? I only see 1 2 here, and there I had 2 2's. Now, the argument is, the property says if I take that 2 and multiply it through both parts here, I will see it both parts here. This originally was just 2 times 8 over 8. And of course the 8's would cancel, giving me 2. But I can break the 8 into 3 plus 5, and because the multiplication distributes across, this is a 6, this is a 10, this is still my 2 times 3 plus 5. That was going to give me 16, and here I get the 16. So I guess what I'm asking is if you are not bothered by the fact I had 2 here and a 2 here, but only 1 2 there, isn't this equivalent? I had an m plus n and an m plus n, but I pulled them out together. Distributive property. Okay, your look gives me the feeling you're okay now. Other questions here? And that, by the way, is a very, it's a very important thing to talk about here, because what seems comfortable with numbers doesn't seem so comfortable with the letters, right? So how can you develop a comfort level? Where did something go? Go back and look at the numbers and say, what happened there? Did I feel okay with that? Well, it's the same thing up here. And maybe that will provide a zone where you say, okay. Now I'm looking at that on the screen, on the monitor. That was supposed to bring understanding. I've got more arrows, arcs, things written, and I'm not sure it is providing the clarity I want, but at least the expression's better, so that I feel good about that. Not the mathematical expression, but Jennifer's smile. So that's better. Any other question on this particular problem or any of the other homework? Yes, another question.
Number 7.
Number 7, could you tell me what it says, since I'm very far from the desk?
4x squared.
4x squared in the numerator? Or just 4x squared?
No, 4x squared.
Okay, a 4x squared and
3x
where does the 3x plus 5 go? On the
Over.
denominator.
Yeah, 4x squared over.
So I have 3x plus 5. Have I written it correctly now?
Yeah.
That's number 7. Now, what do my directions tell me to do? What do the directions in the problem say? What am I supposed to do?
find any values of which each rational expression is undefined.
Okay, so when is a rational expression undefined? When the denominator is 0. So to answer the question, what values of x make this expression undefined? Set 3x plus 5 equal to 0. True? And then what? Solve for x. When x is minus 5 over 3, the denominator will be 0. This is the value that will make the denominator 0. That is then the value that makes the rational expression undefined, because I'm not allowed to divide by 0. Okay? Anybody else on this one? Or any others? Okay. Debbie, let's go back to the document cam for a moment. That's how we got started in this particular problem, which was number 61, and I'm hoping that the questions are resolved a little bit better. And again, things can't be taken out of context here. The context, ultimately, is to take an expression, typically, and try to simplify it. That's the first goal. Just like we reduce a fraction, a numerical fraction. 4 over 8, we want to reduce to 1/2. But typically, these expressions we are seeing are going to be parts of equations. Now, reminder to you. Remember where we had the problems about the triangle? And we found solutions that were negative numbers, and so the height or the base or the length of a rectangle was going to have to be negative, and we said that number can't be used because you can't have length as a negative number. So we had a restricted domain. We mentioned the idea of a restriction at that point. When you get an equation that you're going to be solving, you have to be careful that you restrict the domain first, so that when you get an answer, you're very comfortable that it was not one of the restricted values. So again, we are going to solve equations just like we've done in the past. But the difference will be that the solution will have to be checked against the restrictions. Now I'm going to give you a problem related to that, and I'm trying to think how I want to do the transition here, Debbie. Write down this expression for me. X squared minus 2x plus 1 all over x minus 1. And I want that to equal 0. This time I want an equation. So x squared minus 2x plus 1 is in the numerator. The denominator is x minus 1. And I want that rational expression set equal to 0. Play with it for 30 seconds. Solve it if you can. Simplify it, then solve it. And we'll see what happens. I'm going to see if there's anything like that in the problems that we are looking at. Let's see. I see something reasonably close. What I'm asking you to write is something a little bit like 41. Let's look at that, Debbie. Very similar. You have a trinomial on the top, a binomial on the bottom. You're going to try to simplify it. So even though that's a little more complicated than the one I wanted you to write, let me write what I have given you as a problem. Now first, here's my expression. Now a comment, that's where we are right now. And I'm asking, where are we going? So my question is, if I had an equation, what would the solution be? Is there any value that will make that fraction 0? Well, what's the first thing you have to do? Set x minus 1 equal to 0. Why? You have to check restrictions. So what's your restriction? Okay, the restriction is x not equal to 1, because x minus 1 would be 0. Now, what do you then do? You take the numerator and you factor it. You have the denominator factored. And this is all to equal 0, correct? What would you now do? You've made the restriction x cannot equal 1.
Cancel.
So I can cancel what? Those. And now I'm saying x minus 1 is equal to 0, therefore x equals 1, and I've got a solution. However, I said at the beginning x could not equal 1. Do I have a solution?
No.
No. It just looked like I had a solution. Therefore, no solution. Now that's the kind of thing we have to be careful about. We state our restrictions, and I could have made this more realistic. I could have said x plus 3 times this mess. And then I would have had x equals minus 3, x equals 1, 2 solutions, when in reality I only have what? 1 solution. We have a name for those solutions that is a misnomer in some ways: extraneous solutions. Not icky, extraneous, like extra solutions. Well, if they're extra, how come they aren't? Well, they just look like solutions. So extraneous. They aren't really solutions. They just look like they're solutions. So you do have to be careful of your restrictions. Extraneous.
Right.
Extraneous. An extraneous solution. Okay. We'll just leave that up there, Debbie. I think I'm just going to walk over to the front of the room. Are we ready now to turn those papers in? Oh, yeah. Okay. And I didn't get your set to get back to you today. I just ran out of hours. So I'll try to double up tomorrow and get things back to you. I'm sorry about that. But we get to move on. Okay. When you multiply fractions together in arithmetic, A over B times C over D. So you have A over C times B over D. You just multiply the numbers in the top, multiply the numbers in the bottom, and reduce. That's one way of playing the game. So if A over B times C over D, you just multiply the things in the top, multiply the garbage in the bottom, and reduce it at the end. What's the shortcut we do typically in between? Cross cancel. Agreed? Interesting little example is given here on this first one on page 363. Okay, it's right in the center of the book. 3 over 10 times 5 over 9. You could just say it's 3 times 5 over 10 times 9. 15 over 90. But then what would you have to do? Reduce. So rather than do that, I suspect most of you don't feel as comfortable as I'd like you to with this next part. You would cross cancel. I know, sure as I'm sitting here, you'd say 5 into 5 and 5 into 10, 3 into 3 and 3 into 9. You just take these parts right here and cross cancel, and the 5 and the 10. But notice what we did instead. Prime factored. 2 times 5, 3 times 3. You have nothing but primes. Technically, that 1 could be left out for a moment. Then what happens to the 3 and the 5? Your prime factors cancel, and you're left with 1 over 6. That is what we are going to do. We're going to factor and then reduce. And we're going to have fun. I mean, this is good stuff. Let's see. Yes. I mean, this just has got to make you have goosebumps nearly. Well, okay, let's try. Debbie, let's cut to there. That's a neat looking expression.
Oh.
No, but that should just be such fun. I mean, you're factoring now, and you're good at it. And so how could you see something like this without seeing factors? X squared plus 3x over. We have x squared minus 3x minus 4 times x squared minus 5x plus 4, and in the denominator, x squared plus 2x minus 3. Now, when you see those, some of them are going to seem easier than other parts. Remember, you can sometimes get hints for the factoring because something else was easily factored. Case in point, x squared plus 3x. The others are trinomials. That's just a binomial. And I hope it occurs to you, and I'll just write this up here for the moment, that you have x times x plus 3. Now what does that say? Somewhere else you might find a what? An x plus 3, if you're going to cancel. Well, which of these two trinomials is a candidate for having something with an x plus 3? This one here, agreed? Because it ends with a 3. So you say, well, maybe if I wrote the x plus 3 there, I'd find something that works. What would I need for this missing factor? The x minus 1? It's the only way I get what? A negative 3. Did it work? Yes. Right? Okay, let's keep playing this same game. You can't cancel anything but the x plus 3's here, correct? But there's maybe something here I could cancel with what? The x minus 1. I don't have a guarantee, but I can play the game, what if, and ask. Would there be anything I could multiply times x minus 1 and get? X squared minus 5x plus 4. What's your answer? X minus 4, correct? And that worked. However, if you got an x minus 4, maybe down here, if it's been rigged well, you might have an x minus 4. What would this have to be if that were an x minus 4? You'd have to have a plus 1, right? And an x. Does it work? Does x plus 1 times x minus 4 give you that trinomial? Now, doesn't that make you feel warm and fuzzy? But these problems typically are rigged. So they work. Otherwise, you couldn't cancel. So you have an advantage that if they're going to be nice problems, these are little hints that you can use. Now what are we going to do? Okay, restriction time. You can't have fun yet. See, the fun is when you get to slice everything up. Slice and dice, cancel it out. Restrictions. Okay. Now at this point, do you have to set all these denominators equal to 0? I hope not. You just look and say, aha, x cannot equal minus 1. Aha! X cannot equal 4. X cannot equal negative 3. I have 3 restrictions. And an x not equal to 1. 4 of them. I thought that was a duplicate. It isn't. So I have 4 restrictions. Now that that's done, now you can have fun. This is the payoff. Don't get carried away. Not everything has to cancel here, but it might. Okay, I see an x minus 1 and an x minus 1. Am I cross-canceling? No, but that's okay. The same factor is in the numerator as in the denominator. So I get to do that and a 1. And I do this and a 1. Now, I'm a little bit concerned that you write in the 1s, because if everything cancels, you don't get 0. You get 1s. What about the x plus 3? Way up there, right? That's good. The same factor cancels. And then we said what? That x minus 4. Now, what's the only thing I have left? The x in the numerator and x plus 1 here. What's the danger? Getting so enthusiastic. You say, an x, another x, goodbye. No, because this x is a what? A term, not a factor. And sometimes putting parentheses around that x plus 1 keeps you from making the foolish mistake. Got it? Let's look at the one we had in the document cam again. There's the problem, and now here's what we did with it. Okay, back to the document cam. Now, can you imagine that you'd have that much fun doing an expression like that and feeling maybe a little bit of good goosebumps? Okay. You aren't responding to that question. Let's see if things get any messier. Oh, division. Okay. No. Don't go saying, oh my God. This is not the response I want. It's going, all right, is the response I want. Let's see if we can get something that looks good here. Trying to get something that has a little bit more with x's and z's and things. I get tired of the m's and... there's a nice one. 36. No, that's not good because that's another multiplication. So let's go down to 38. There's a nice division. I'll just slide that up. 38. Oh, there's so many nice ones there, it's hard to choose. 38. Okay. By the way, what was the problem we just had on the board? Oh, an example, an EX. Okay. This is number 38. Is that what I agreed to? Okay. R squared plus R minus 6 over. And we have R squared plus 4R minus 12. Is that right? And then we have it divided by R plus 3 and R minus 1. There's only one important issue, first step. Never cancel when it's written as a division. What must be done first? Rewrite it as a multiplication. And the infamous phrase, invert and multiply. Divide and conquer. Invert and multiply. This may seem like a little bit unnecessary, and even as I do this, sit there and think, God, this is wasting some space, but I think we better take time to do it. I rewrote it as a multiplication. Don't sit there and slice out the r plus 3 and replace it with an r minus 1 and slice out the r minus 1 and replace it with r plus 3. Rewrite it. Now, factor time. Playtime, factor time. Okay, if there is justice again. Now, you could look at r squared plus r minus 6 and say, I see it. But what's the hint? Maybe an r plus 3. Just maybe. So if I had r plus 3 here, could I have an r minus something that would make it work? How about a minus 2? An r minus 2 because I need a negative 6? Does it work? And maybe, let's see. Debbie, let's try doing cameras 1 and 2. Take one and maybe just zoom in just on that little, because people who are watching it in the video may not have quite the... You just want the numerator on the left side? Yeah, just that little part there. You just zoom in. There we go. Isn't that neat? I love technology. Okay, r plus 3 times r minus 2. And as we come back here, I'm going to make sure I write that as r minus 1 as a binomial. And then I have 3 choices here to help me do what down here? To factor this. Now, I don't know if any of this will work, but the r plus 3 is gone. Maybe an r minus 2 here. Why not the r minus 1? I look at the 1 and the 12, and there's no way I'm going to get 4. That's why I'm looking at this and saying, if there is anything that's going to work, it's going to have an r minus 2 here. Well, if that's the case, what's going to have to be here? An r and a 6. And to get the positive, I'm going to need that. Did it work? Thank you, Debbie. Does it work? Yeah, you get 4r in the middle. Isn't that neat? You let the problem work for you. Now, while it's just like it is on the screen, let's come back to that. That was nice. Can you now just see, there's just an uncontrollable urge to cancel some things? You have to restrict yourself for a moment. Because restriction time. What are the restrictions? Okay, now we've got to be really careful here. Because note, in the original problem, r minus 1 was in a denominator, so r cannot equal what? Could not equal 1 because that would have given us a 0 in the original fraction. And r cannot equal what? Cannot equal, well, we can come back here, the negative 3. And then r not equal to the negative 6. And the r not equal to 2. We've really restricted ourselves here. Let's drop just a smidge to pull in or zoom a little. There we go. Those are the restrictions. Now are we ready to have fun? Okay. An r plus 3 and an r plus 3. An r minus 2 and an r minus 2. And what does it give us for an answer?
R minus 1.
R minus 1
Over R plus 6.
R plus 6. And you cannot cancel the r's because they are terms, not factors. Okay, let's go back and look at the original problem on the document cam. It's intimidating, right? And your first reaction may be to run out of the room. But these can be fun. Okay.
Let's not have too much fun.
Well, I didn't even get to the really fun problem.
I see it.
It's just sitting there demanding a look.
45.
Come look. 40. Now look.
Okay, let's go to 45.
I knew you were going to look at that one.
Isn't that neat?
That's easy.
What you must do is simplify what's in the big parentheses before you invert it. Okay? That's a neat problem. So we will try to restrain. Not a lot. Okay, let's see what we can have. Starting with number 3 and going through. Boy, this is... How far do we want to go? We've got to do something in that 45 range.
Sure.
How about number 3 through 50 odds? 3 through 50 odd numbers. Debbie, I can't wait to hear your choice for music of this helplessly hoping we started, but now we're full of confidence, and?
I picked Guinevere because that sounded fun, and you just had so much fun today.
Guinevere. Okay, there's a lot of images that come through my head with that, but we'll go with that. Have a great morning.